morning children, and welcome back to your chemistry class. Today in this classification of elements, we are going to study about the periodic trends in the properties of the elements. So firstly we should understand what do we mean by this periodic trends, right? So the regular increase or decrease in the properties of such as ionization enthalpy or electron gain enthalpy or even atomic radii or valency of electrons across a period and along a group of the periodic table, that is termed as periodic trend. Okay, so the periodic trend in properties of elements, it is governed by electronic configuration. So today we are going to study how the periodic trend in electronic configuration of elements happens across a period and down the group. We are first going to talk about today the periodic trends in electronic configuration of elements. Okay, so over here I'm going to divide this page and we are going to discuss about group and period. This is going to make the study more simple when we are going to compare the groups and the periods. The elements of the period, they have different electronic configurations in their valence shells, but the number of shells, they are always the same for all the elements of the same period. So what is a period first and foremost? When we move from left to right. Okay, so let us take an example of period 2. Okay, so the electronic configuration of lithium, which is 3, is what? 1s2 2s1. That of fluorine is what? 9. It is 1s2 2s2 2p5. Okay, then let us talk about neon, which is 10. The configuration will be 1s2 2s2 2p6. So for each element of this period 2, the valence shell is the same. What is the valence shell? N will be always 2. N is always 2. But the number of valence electron is different. Look over here. Here for lithium it is 1. For fluorine it is 5. For neon it is 6. Okay. So for the electronic configuration of the elements in the period, we find that the number of valence electron, it increases from 1 to 8 on moving from left to right. The first element always contains 1 electron, ns1, in its valence shell, and therefore this belongs to which group? This is your alkali metal. The last element which contains 8 electrons, that is ns2 np6. Okay, so its valence shell, in its valence shell, then this is your noble gas. So in period we started from alkali metal and we end up with the noble gas. Clear? In period 1 we start with hydrogen and we end up with the last element, that is helium. So there are only 2 electrons present in your first period. So I hope this much is clear about the electronic configuration. Now let us talk about the group. All the elements of a group, they have similar electronic configuration in their outermost shell. But the electronic configuration of the outermost shell of an element in one group, it is different from that of the other group. So let us take an example over here also. Look at group 1 element. So over here lithium, if you configure it is 1s2 2s1. Okay, Then for sodium, if you configure it is 1s2, 2s2, 2p6, 3s1. For potassium, if you configure you get 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So what did you see? If I am going to see the condensed configuration also, let us write down the condensed configuration. There also let us check. Helium is 2. So we can write this as helium 2s1. This can be written as neon 3s1. This can be written as argon 4s1. So what are we seeing over here? Of electrons in the outermost shell remains the same. Is that clear? Thus, we say that the electronic configuration in a group, it always remains the same. Now let us take group 2 and then let us see the difference between the electronic configuration of group 1 and group 2. So over here, if we take beryllium is 4. Okay, so configure 1s2, 2s2, and if you configure it in a condensed configuration, then it becomes helium 2s2. Then let's see magnesium. Magnesium is 12. So 1s2, 2s2, 2p6, 3s2. Okay, or what else can be written as neon 3s2. Then calcium, which is 20. So it can be written as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, which can also be written as argon 4s2. So look over here. When in the outermost shell you see one electron, then it is from group 1 and they all have similar electronic configuration. Group 2, they all have 2 electrons in the outermost shell. They have similar electronic configuration. But the 2 different groups, they have different electronic configuration. I hope till here it's clear. Now let us talk about the periodic trend in the valency of electrons. Periodic trend in the valency of elements. Okay, so if you look at the period, right? So if I have taken period 2 elements, let me write down all the period 2 elements, like for example lithium, then beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Okay, their atomic numbers are 3, 4, 5, 6, 7, 8, 9 and 10. Okay, and let us configure them. So this is what, as we had already done. So now let us look at their valence electrons, okay, in each of them. So in lithium, the valence electron is how much? Valence electron is 1. In beryllium, valence electron is how much? 2. Boron, it is 3. Carbon, it is 4. Nitrogen, it is 5. Oxygen, it is 6. Fluorine, it is 7. And neon, it is 8. So what do we know about the valency then? This will be +1, this will be +2, this is +3, this is ±4, isn't it? This is the valency will be what? Therefore, valency will be +1, +2, +3, this will be ±4. If this is 5, then this becomes -3. If it is 6, then it is -2, -1 and 0. So what do we study about the valency? What is the periodic trend in the valency of elements in a period? So as we move from left to right, we see that the valency first increases from 1 to 4 and then decreases back to 1, right? And then it becomes 0 in case of noble gases. I hope this is clear about valency. Now let us look about the valency in a group. In a group, all the elements in that same group, they have the same normal valency. Look at group 1. All of them have 1 electron in the outermost shell. That means they can lose that 1 electron. So that is their valency. So all the elements in that group 1, they are going to have valency +1. All the elements found in group 2, they have 2 electrons in the outermost shell. That means they are going to lose 2 electrons. So all of them will have +2 as their valency. Here it is +1 as the valency. So in a group, all the elements, they have similar valencies. Is this clear to all? Now let us talk about the periodic trend of ionization enthalpy or potential. Okay, so what is ionization enthalpy? It is defined as the minimum amount of energy required to remove the most loosely bound electron, okay, from an isolated neutral gaseous atom resulting in the formation of positive ion, right? Over here, that is, if this is the isolated neutral gaseous atom, right, it needs energy, okay, and then it gives away the electron to form a cation or a positive ion. Is that clear? And this is always expressed in electron volt per atom, right? Or it can also be in kilocalories per mole, right? Now when it loses electron from a parent atom, it converts into a cation. This cation means inward pull increases. So for removal of the second electron, more energy is required. Similarly, more energy will be required to remove the third electron. So this is called as successive ionization enthalpy, right? Where what? The first ionization enthalpy is related to the removal of one electron from the valence shell of the gaseous atom, and then it is possible to remove second or even third or even more electrons from the same atom. So energies are required to remove the subsequent electrons, and thus we can say that these energies, to remove the second electron, the third electron or the fourth electron, in general we call them as successive ionization enthalpy, right? And they are denoted like IE1 or IE2 for the second ionization energy, then IE3 for the third successive ionization enthalpy, and so on. Clear? So how do we get to understand this? You may understand more clearly, like suppose this is a gaseous atom, okay, isolated neutral gaseous atom, where it requires first ionization energy to convert itself into a monovalent cation and one electron is taken out. Now, this particular cation, it has more electrons, so it requires more energy to remove the electron, and thus it forms a divalent cation and the electron is removed. Now from this divalent, more energy will be needed to remove the electron and it forms a trivalent. Are you getting my point? And hence we can say over here that in general the successive ionization energy, it shows an increasing trend for the same atom, and hence IE4 will be greater than the third ionization energy, than the second ionization energy, and least will be for the first ionization energy. Clear? Now let us understand what are the factors that affect the ionization enthalpy. Factors affecting ionization enthalpy. The first is size of an atom. Always remember, larger this atomic size, smaller will be the value of ionization enthalpy. So we can say that ionization enthalpy is inversely proportional to atomic size. Clear? Then second point, screening effect. Screening effect. Now what do we mean by screening effect? Okay. What do we mean by screening effect? Screening effect also means shielding effect, right? That is, in a multi-electron atom, the electrons that are present between the nucleus and the valence electron, right, they shield the valence electrons from the nucleus. Now suppose this is the nucleus which has protons and electrons, and this is the first shell which has 2 electrons. Suppose this has 8 electrons and the outermost shell has 2 electrons. Okay, and there are 8 electrons present over here. 1, 2, 3, 4, 5, 6, 7 and 8 electrons over here and 2 electrons here. So what did I say? That it is a multi-electron atom, right? Over here the electrons which are present between the nucleus and the valence shell. Okay, these electrons, what do? They shield the valence electrons from the nucleus. So this decreases the effect of the nucleus on the valence electron, right? Due to these electrons who are shielding these 2 electrons on the valence shell, what happens? These valence electrons, they have less effect on the nucleus, or we can say this decreases the effect of nucleus on the valence electron. Therefore, the nucleus exerts less force of attraction on the valence electrons, and this is termed as shielding effect or screening effect. Clear? So what did we study about the screening effect over here? That higher the screening effect, lesser is the value of ionization enthalpy. Why so? As the screening effect, it will always reduce the force of attraction towards the nucleus, so that the outer electrons, they are removed easily. So over here, ionization enthalpy is always inversely proportional to what? Your screening effect. Right? Then we come to nuclear charge. Your ionization enthalpy also depends upon nuclear charge. What is that? Greater the nuclear charge, higher will be the ionization enthalpy of an atom. Remember, so ionization energy is directly proportional to nuclear charge. More the nuclear charge, more will be the ionization enthalpy. Less the nuclear charge, less will be the ionization enthalpy. Then the fourth point is electronic configuration. Electronic configuration of atoms. Now here what? Atoms or ions, they have stable electronic configuration and they have unexpectedly high ionization enthalpy, right? For example, the first ionization enthalpy of a nitrogen atom will always be higher than that of the oxygen atom. Why? Because in nitrogen atom, the p orbitals, they are half filled. Atoms or ions having stable configuration, okay, they have unexpectedly high ionization enthalpy, right? What do we mean by stable configuration? That is, either it is half filled, orbitals are half filled, or the orbitals are completely filled. Then only they are stable, isn't it? So let's take an example of nitrogen atom. Let's take an example of nitrogen atom and oxygen atom. Okay, so look at nitrogen atom. The configuration will be 1s2, 2s2, 2p3, whereas that of oxygen is what? 1s2, 2s2, 2p4. So first ionization enthalpy of nitrogen is always higher than that of oxygen. Is that clear? Why? If you check this 2p, it has 3 electrons, 1, 2, 3. This is half filled. Whereas if you look for 2p4 over here, then it is 1, 2, 3 and 4. It is neither half filled nor completely filled. So ionization enthalpy of nitrogen will be always higher than that of oxygen atom. Then the fifth point, that is the penetration effect of electrons. Now, the s orbital is more close to nucleus than the p orbital of the same orbit. Thus, the p electrons can be easily removed in comparison to the s orbital electrons. Therefore, the penetration power of various electrons, it varies in the order of what? S, P, D and F. This also means that an s electron has a greater chance of being closer to the nucleus and therefore experiences more of the nuclear pull than the p electron. Therefore, greater energy will be required to remove s electron than to remove the p electron. In other words, we can say that greater the penetration of electron, more is the ionization enthalpy required. So I hope all the factors are clear to you. The successive ionization enthalpy is clear to you. Now we are going to understand the trend of this ionization enthalpy of elements across the period and in the group. Now let me divide it into two. That is, we are going to discuss about the ionization enthalpy in the group and in period. So let us talk about the variation in the group. So in the group we know that as we go down, what happens? Firstly, there is increase in the size of an atom. Secondly, what else do we know? The screening effect also increases. Screening effect increases as we go down the group, right? So what will happen? Therefore, the ionization enthalpies, they decrease in the group when we move from top to bottom. Therefore, ionization enthalpy decreases when we move from top to bottom. There is an exception to this trend after the element with atomic number 71. That is atomic number 72 to atomic number 82. There is an exception due to lanthanide contraction. Over here we observe lanthanide contraction. Okay, this will be explained to you later. The ionization enthalpies of the inert gases are exceptionally high due to their stable configuration because they are fully filled orbitals. Okay, so over here what did we study? That down the group, since there is increase in the size and the screening effect is also more, therefore ionization energy decreases. But there is an exception. What? Between atomic number 72 to atomic number 82. It shows lanthanide contraction. Okay, and the ionization enthalpies of inert gases is always high, are exceptionally high. Why? Because they have stable configuration. Due to their stable configuration, right? They have fully filled orbitals. Now let us talk about variation in a period. In a period, what do we know? As we move from left to right, the ionization enthalpy increases. Ionization enthalpy increases from left to right. Now, first reason, because nuclear charge increases. So we had studied that nuclear charge increases, which is directly proportional to ionization enthalpy. So ionization enthalpy increases because nuclear charge increases. Okay, then there is decrease in the atomic radii, which also increases the force of attraction towards the nucleus. So this was the first factor that we had discussed, that atomic size is inversely proportional to ionization enthalpy. So over here, since atomic size decreases, therefore ionization enthalpy will also increase. I hope you know why the atomic size decreases, because the number of shell remains the same, the nuclear pull increases, therefore atomic size decreases, and then ionization energy increases over here. Clear? So high energy is required to remove the electrons, and hence ionization enthalpies, they increase this side. Now certain exceptions over here also we need to understand. In the ionization enthalpies, the first ionization enthalpy of beryllium, first ionization enthalpy of beryllium is always higher than that of boron. Nitrogen, as I have already told you, is higher than that of oxygen, and even that of magnesium is higher than aluminium, and even phosphorus, the first ionization enthalpy of phosphorus is higher than sulfur. These are some of the exceptions that you need to remember. So I wind up over here with ionization enthalpy. We'll study about the other periodic trends in the properties of elements in the next video. Thank you.